One thing that occurred to me after stopping the recording on the last video, in regards to the cube root function, if you ever get stuck, you just can't remember, this is a really pretty simple one to just plot some points. Just pick an input and then see what output it produces. If you take the cube root of 0, you're going to get 0. The cube root of 1 is 1. The cube root of negative 1 is negative 1. Okay. And then the next one, you wouldn't want to pick 2 or 3 or 4. You'd pick the next convenient value, for x, in which you'd have a perfect cube root. And that would be 8. The cube root of 8 is 2. The cube root of negative 8 then would be negative 2. And so you can see we got close. And again, 8, 2, what did I say? Yeah, just, you can, if you had to plot points, you could do that. 1, 1, we got that one right on it. Just want you to get the general shape of these graphs, okay guys? And negative 1, negative 1, a little off there. And then negative 8, negative 2, a really big dot for that one. If you need to plot points like that, then there you go. So you can see generally why that shape of the graph is what it is. So I just wanted to point that out. If you ever get stuck, you just can't remember, and don't think that this stops there, it just keeps going forever. And then just plot points. Pick the input, see what output it produces, and then plot the ordered pair as a dot, and then connect the dots. So we did page 14 and then page 15. Brings us to page 16, which is the rational function family. And by the way, let's see, let me get you a riddle here. Here's your next riddle. I am a man. If Jason's son is my son's father, what relationship am I to Jason? Pause the video. I'm going to say the answer right now. If you want to think about it, pause the video. So the answer is you would be Jason's son. Okay? You would be Jason's son. That is the answer. Alright. Function family. We have talked about these functions. We're in the rational function family. And the parent function would be y equals 1 over x. And just like this start of this video, and I was talking about just plotting points, just pick some. We know that based on what we know about rational functions, we know that x can't be 0. That does not exist. In fact, x equals 0 is a vertical asymptote. And let's pick 1. So x equals 1, we get 1. X equals 2, we get 1/2. 3, we get 1/3. So you can see as the x gets bigger, the y gets smaller, but still positive. Okay, so we can plot a couple of those points. 1, 1. 2, 1/2, 3, 1/3, 4, 1/4, and so forth. But then if we just pick, let's say 1/2, 1 divided by 1/2 is 2, 1/3, 3, 1/4 is 4, and so forth. So we should be able to see that our graph is climbing right up there. And don't forget, we also know that this function has a vertical asymptote. This should be a pretty easy review for you. And I wish I had my red. I really wish I did. Okay, well I don't, so that's the way it goes. I'm going to draw this curve in purple. It's not as distinguishing of a color, but nevertheless. So we know what these look like. We've studied these. We could also pick some negative values for x. Let's just draw another x and y chart. And if we pick -1, we'd get -1, -2, -1/2. And we could do the same thing by choosing different values for x, -1/2, -2, -1/3, -3, and so forth. And we would see that we get a mirror image about the origin, mirror image of what we just drew up there, and we get your graph of y equals 1 over x. Okay, so we get a little bit more of an interesting graph than the last one. where we have a domain that does not include all real numbers. The domain would be all real numbers except for 0. X such that x cannot be equal to 0. It's a good review from what we've done this semester. The range is also, as you can see from the graph, the y values that are being used to draw the graph are every single one from negative infinity all the way to positive infinity except for y equals 0. So we say that all values of y such that y does not equal 0. And you could write that in interval notation. I'll let you decide how you want to do that. Increasing, you can see as you move your way along the domain, never are the y values getting any bigger, and so we say no intervals. But we do see that the y values are getting smaller all the way from negative infinity to 0, not including 0. And you can put a union symbol there as well. But they're also decreasing on the interval from 0 to infinity. Okay. Horizontal asymptotes. Even though we didn't draw a horizontal asymptote, we know, based on what we know about rational functions, that the horizontal asymptote is y equals 0. Okay, so y equals 0 is our horizontal asymptote. And why is that? Yeah, I don't know if you remember this or not, but we defined a horizontal asymptote if the denominator, as x gets really, really big, if the denominator is getting bigger than the numerator, then we see that the values of y are getting smaller and smaller, and they're approaching a real number. And as long as they're approaching a real number, as x gets large, positive or negative, that real number, y equaling that real number, is our horizontal asymptote. So an excellent review, because I do remember going over this with you guys. So vertical asymptote, we already talked about that x equals 0. Whatever x makes the denominator equal to 0 is our vertical asymptote. We have no x-intercepts, and we have no y-intercepts either. And again, we have no max or min. So there you go. Let's go ahead and cruise on over to, I didn't write this down, but this is page 16. Okay, so that's the rational parent, y equals 1 over x, page 16. Now let's go ahead and have you pause the video after I show you what the transformation is. Again, this is rational, and the transformation is y equals negative 3 over x plus 2. Well, the negative 3, that constant in the numerator isn't really going to change anything other than let's just plot some points. Let's think first. That's always good. When we graphed y equals 1 over x, we knew what that looked like. Okay, and let's graph y equals negative 1 over x. Okay, negative 1 over x. And if we graph y equals negative 1 over x, that we take 1 over x and we reflect it about what axis? Well, we reflect it about the x-axis. It's an up and down. Okay, so this is the original graph. And then if we reflect about the x-axis, we get a graph that looks like this. Okay. And you can get away with reflecting about the x or the y-axis for this one and still get the same value. And then we're going to replace x with x plus 2. So if we replace x with x plus 2, it means we take this current graph, the green one, and we move it to the left 2 units. So we go 1, 2, and that means we're going to move our asymptote. And then that's it. Move the asymptote, and the green graph that moves to the left 2 units, and it goes like this. The 3 really does nothing. It's just a multiplier. Don't let that bother you. That's what it looks like. Okay. You always want to confirm. It's really good to do that. Sorry, let's make an XY chart. And if we make an XY chart, let's pick values like 0 for x, and then we get negative 3 halves. Look down here, pretty close. That's good. How about a convenient value for x? How about, let's say, 1? And if we plug 1 in for x, we get negative 3 over 3, which is negative 1. And so 1, negative 1, yep, goes right through that. Let's pick a value to the left of the vertical asymptote. So how about negative 3? Okay, negative 3. And if we pick negative 3, we get negative 3 plus 2 is negative 1. So we get negative 3 over negative 1, which is 3. So negative 3, 3 goes right through it. So pretty confident that we got the exact graph. If you get a few points on there and you draw the graph, and you can be pretty sure. And I know that when you're in a hurry on a test, you don't want to take a lot of time to do these, but you want to try to be sure, as sure as you can on your graph. Okay, so let's look at the characteristics. Let's see if I can squeeze this in. I hope the video doesn't die on me. So all real numbers x, such that x does not equal negative 2. There's our domain. Our range is all real numbers y, such that y does not equal 0, because 0 again is a horizontal asymptote. Increasing now, this function is increasing all the way from negative infinity to negative 2, combined with the interval from negative 2 to infinity. It's decreasing nowhere. Horizontal asymptote, yeah, we've got y equals 0. Make sure you put a y there for the horizontal. And the vertical, x equals negative 2. Okay, the x-intercepts, no x-intercepts. But we do have a y-intercept, and we just have to let x equal 0 for that, negative 3 halves. And again, no max and no min. Let's see, did I give you guys? Yeah, you're good. See you next video.